Okay, let's finish Module 5. We're going to cover atomic mass, molecular mass, the mole concept, and how to use that mole concept to do chemistry. So that's what's left for this module. I want you to take out your periodic table, or periodic table of the elements, whatever you want to call it. You need it for this module and for the next one and so on. You're going to be using it from now on. But here we go. I want you to notice the little squares. We talked about the little squares a tiny bit before, but I want you to notice that the little squares have two numbers. Okay, the top number, sometimes it's in the middle right here, is the atomic number. The atomic number is the number of protons for that specific element, and it defines the element. That means that the only element that has 10 protons, or atomic number 10, is neon. If somebody gives you an atomic number, for example, number 12, you can go to the periodic table and say, oh, we're talking about magnesium. So it's specific for that element. It defines that element. And we have not talked much about protons, electrons, and neutrons yet, but we will. But you should be familiar because you took the protons, electrons, and neutrons. You should be familiar with them because you took physical science before you took chemistry. But anyway, let's continue. Your periodic table does not have the name of the element. It only has the symbol, the chemical symbol. You are memorizing them in groups of 20. Eventually, you're going to know the whole table. I want you to know the whole table because you will be needing to quickly go from a name. They will say to you rubidium, and you need to be able to write RB when you're writing a chemical reaction. So you need to be able to do stuff like that. And this is the second number. We're going to be concentrating on this number right here. What is this right here? Well, this is called the atomic mass. So the mass for that specific element. In this case, neon. So the mass for an atom of neon is 20.180. Now, you're going to need to use the number that's given to you in your periodic table. Different periodic tables have different numbers after the decimal point. So to do the math for this course, you will use the one provided in the textbook. The atomic mass is not in grams. That should make sense to you. Atoms are very, very tiny. So the atomic mass is measured in what's called the AMU. Here you have it. AMU is just atomic mass unit. It's a unit specific to measure the mass of atoms. That's all it is. So atomic mass units is AMU. And sometimes I call it AMU just to go faster, but know that I'm talking about AMUs. Now, more information. One atomic mass unit is the same as 1.66 times 10 to the minus 24 grams. Do you need to memorize this conversion factor? No. This is going to be given to you when you do your problems. It's an average. Let me go back for a minute. We said that the atomic mass was an average. What does that mean? An average is because not all the atoms for neon, for example, measure that. Okay, some are heavier than others, and we'll be talking about isotopes in a different module. But anyway, just know that not all atoms are the same. They have the same atomic number. That's why they are neons. But some of them have more neutrons than others, and they weigh more than others. So when you average their mass, that's what that number comes from. It's an average of the different masses of different atoms of neon. Let's look at the periodic table for a second. I think that's all I have to talk about in here. Yes, that's all we're going to cover. Okay. So what else do you need to know about the atomic mass unit? Besides its abbreviation, AMU, and that you can find that number in the periodic table, the bottom number, is that is equal to the mass of one proton. You need to know that. One atomic mass unit, one of them, is equal to the mass of 1 proton. Okay. Now, with this information, what do you need to be able to do? Let's look at this example. Example 5.4 on page 143 plus. They'll ask you questions like this. What is the mass of a nitrogen atom in grams? Okay? And they give you the conversion factor between AMUs and grams. So let's go to the blackboard here and write down what they're saying to us. They said nitrogen. The atom is nitrogen. So you need to go to the periodic table. You go to the periodic table. I'm already telling you that it's in position 7. Please notice that each box is organized in increasing atomic number. So start with hydrogen having number 1, helium number 2, lithium number 3, beryllium number 4, and then boron on the other side with number 5, and so on. So it increases from left to right and from top to bottom. So they're all organized in increasing numbers, atomic numbers, so number of protons. So nitrogen is in position 7, is in the square that says 7. So if you look at your periodic table, in the box that says 7, you can find the atomic mass unit for nitrogen, and it says that it is 14.0 atomic mass units. Anytime that we are changing units, we open our factor level method, we put the unit that we're trying to get rid of at the bottom and the new unit that we want at the top. So we can cross it like this. They give you the factor. The conversion factor is given to you in the problem. It says that one of them, one atomic mass unit, is the same as 1.66 times 10 to the minus 24 grams. So if you put this in your calculator, and by now you should be pretty good about using your parentheses and using your calculator, you'll be getting this number, 2.32 times 10 to the minus 23 grams. This is your answer, which matches the book. 3 significant figures, 3 and 3 and 3. And you are done. That's the kind of problems that you need to be able to do with this information so far. Now, let me erase this so it's ready for the next problem. Let's go back to instruction. So molecular mass, the mass of a molecule. You can add up the masses of each of the atoms present in the molecule to calculate the mass of the molecule. It's as simple as that. So here you go. The example they give you is this molecule has a sulfur and 2 oxygens. Okay, remember that the subscript tells you how many oxygens you have 2. So you need to add them up. You need to go to the periodic table and find sulfur. So sulfur is in position number 16, and you'll find the atomic mass units for the mass for that sulfur. You can do the same thing for oxygen. If you find oxygen in the periodic table, you'll see that it's in position 8 and it has a mass of 16. Now, that's only for one of them, and this molecule had 2. That's why you had to multiply by 2. If you put this in your calculator, you'll find that the mass for this molecule is 64.07 atomic mass units. So that's the kind of problem you're going to need to be able to do. Okay, let's look at an example. This one goes like this. Then you're going to do extra practice problem number 9. This one has actually 2 sections. The first one is this one. What is the molecular mass of this molecule? And then the second part says, what is the mass? They give another molecule in grams. So we're going to have to do them both. Let's start with this one right here. And then you'll do the practice problem on your own. So let me copy the molecule they give you. Carbon, hydrogen, and chlorine. And they say they have 3 of those. So what is the mass? They want to know the mass of this molecule. What you need to do is find each one of those atoms in your periodic table and start adding their masses. So I'm going to put it right here to have more space. There's 1 carbon. If you go to the periodic table, carbon is in position 6. And the mass in your periodic table is 12.0 atomic mass units or moles. Now we're going to have to add the mass of the hydrogen. Hydrogen position 1 is one of them. And according to your table, the mass is 1.01 atomic mass units. Now, there are 3 chlorines, so you need to multiply the mass of the chlorine by 3 because there's 3 of them. And chlorine is in position 17 in your periodic table. According to your table, the mass of just one is 35.5 atomic mass units. Now, put all of these in your calculator and you'll find that the mass for this molecule is 119.5 atomic mass units. And that's your answer. That's it. That is your answer. I want you to notice that we finish in the 10th position here. Okay, this is an addition right here. So this is 10th position. Is the smallest. Because here's in the 10th positions too, but this one is 100th position where it ends. So you need to go with the smallest position, and that's the 10th position. And you end it in the 10th position as well. Okay, so let's erase this one and do the second part to this example. The molecule they gave you for the second part is this one. There are 6 of these and 12 of these. I'm just copying it. And they also gave you the conversion factor between atomic mass units and, sorry, I forgot the U, and the grams, 1.66 times 10 to the minus 24. You may memorize it if you want to because you're going to be using it so much, but it's going to be given to you every time that you do the problems. Okay. To be able to find the mass in grams for this molecule, I need to first find the atomic mass units, the mass in atomic mass units for this molecule. So I need to use my table and start adding all the masses for each one of these atoms. Let's see. The first one, where you're going to find that silicon is fine in position 14. So you go to periodic table, find silicon in position 14, and there are 6 of them. Okay, so 6 times each one of them weighs 28.1 atomic mass units, AMUs. Okay, great. The next one is your let's see if I find it myself. I have to find it, the position for this one. Fluorine is in position 9. Okay, you're going to find the atomic mass unit for fluorine in the little square that says 9. And it says that there are 12 of them. So each one of them weighs 19.0 atomic mass units. And the last one is your oxygen. And oxygen is in position 8 and is 16 each. There are 6 of them. So multiply that by 16. Oops, I'm going to put AMU, sorry. And close the parentheses, equals. So what is that equal to? Put it in the calculator. You'll find that the mass in atomic mass units for this molecule is 492.6 atomic mass units. But they don't want it in atomic mass units. They want it in grams. I'm just going to open my factor here. I could copy it again and do it at the bottom. I'm just going to go ahead and just open it. And remember, I want to get rid of my AMUs and then with grams. One of them, 1 AMU, equals 1.66 times 10 to the minus 24. This disappears. If I do the math in my calculator, I find out that my grams equal 8.18 times 10 to the minus 22 grams. Okay. And that's how you solve this kind of problem. Okay, you need to find the molecular mass in AMUs, and then you can convert that into grams. Now you're going to do one of these on your own. I'm going to give you the answer. If you get it right, just move on. And if you don't, you can try again. And if you still don't get it, you can watch me solve it for you. But basically, they give you this molecule, potassium 2, carbonate 3, and of course they give you the conversion factor. 1 AMUs equals 1.66 times 10 to the minus 24 grams. They give you these two. These are the two things that they give you, and they want to know the mass in grams for this molecule. So the answer should be 2.29 times 10 to the minus 22 grams. If you got this, move on. This is a video, make it work for you. Just skip this part. And if you didn't get it and you have tried it one more time, here is how it was solved. Okay, we're going to need to add the mass of each one of the atoms in this molecule. That's what we're going to have to do. Okay, so let's start with the potassium. Where are you going to find that? Potassium is in position 19. So according to your periodic table, there are 2 of them, and each one of them weigh 39.1 AMUs. Now, there's one carbon. Carbon is in position 6 in your periodic table. There's only the one, but each one of them weighs 12 AMUs. Okay, problem with my mouse here. And the last one is the oxygen. You have 3 of them. Oxygen is in position 8, and each one of them is 16 AMUs. Put everything in the calculator, and you'll see that this molecule has a mass of 138.2 AMUs. But that's not all they wanted. They wanted this in grams. So we need to open our factor level method here, put the AMUs at the bottom to get rid of them, like this, and end with grams at the top. We read the conversion factor, put it in the right spot. So 1 AMU equals 1.66 times 10 to the minus 24 grams. Use your parentheses if you need to, and then put in the calculator everything. After that, you'll get this number, 2.29 times 10 to the minus 22. Okay, let me erase this so we can continue with instruction. Okay, moving on with instruction. What is a mole? You're going to find the information on page 145 plus in your book. So here it says the mole is a unit that is used to quantitatively measure the amount of substance. So it's a quantity, it's a number. You're familiar with words that mean an amount of something. For example, when you hear the word couple, you know that a couple of bananas means 2 bananas. So the word couple means 2. You're familiar with a dozen, the word a dozen. I need a dozen eggs. In your mind, you say, okay, I need 12 eggs. Mole is the same kind of concept. It stands for a numerical value. So when you say, I have a mole, you have 6.022 times 10 to the 23 atoms or molecules. So it's using chemistry to count atoms and molecules. That would be an enormous amount to count anything else. You're not going to say I have a mole of eggs or a mole of elephants, because that would mean you would have 6.022 times 10 to the 23 elephants or eggs. So no, we use it in chemistry. This number is also known as Avogadro's number. And here's a picture of the man who did research and found this number. Okay, so let's move on. Here's another picture just to emphasize the concept of the mole. I don't remember where I found this cute picture, but it's a quantity, so you're measuring an amount, is a numerical value, 6.02 times 10 to the 23 atoms or molecules. And it would be good for you to kind of memorize these. Now, Why do we need to know about moles? You're going to be doing stoichiometry this year, and we use moles to do stoichiometry, so to do chemistry, to do equations, to calculate things. Two things that you're going to have to memorize and understand and apply. They're in the boxes here. Let's read the first one and try to explain what it says. It says an atom's mass, and remember that you can find the mass of an atom in the periodic table, those are the AMUs, tells you how many grams it takes to have 1 mole of those atoms. So for example, let's go to the periodic table. Find oxygen, position 8. It says that the AMU for oxygen is 16. It says here in this little box, it says that 16, if you don't call it AMUs, if you call it grams, you have 1 mole of that substance. You have 6.022 times 10 to the 23 atoms or molecules. In this case, we're talking about atoms, so you have that amount of atoms. We'll see in a minute how this applies. The same is true for molecules. If you have the molecular mass in AMUs, and if you remember, we did see an example of moles on, let's see, what page was that? On page, oh well, we have not talked about this yet, but on page 147, you have figure 5.3, and in a minute I'm going to go over that with you. But if you look at that figure 5.3 on page 147, you'll see that they give you examples of different things that have a mole of that substance. They have water, sodium chloride, which is stable salt, they have iron, and they have hydrogen. So if you add up the AMUs for all the atoms in the water, you'll see that water has a molecular mass of 18 AMUs. And they're saying, okay, don't call it AMUs, call it grams now. So when you have 18 grams of water, you have 1 mole of molecules of water. And the mole was 6.022 times 10 to the 23 molecules of water in those 18 grams. That's what it's saying. Let's look at more examples on that table. Table salt, sodium chloride. If you add the molecular mass, so all the atoms' masses from the periodic table, so the sodium and the chloride, when you add them all up, you'll see that the molecular mass for sodium chloride is 58.5 AMUs. Well, don't call it AMUs, call it grams. And now you have 1 mole of sodium chloride. The next example is the iron on figure 5.3. Iron is in position 26 in your periodic table. And if you look at the AMUs, the atomic mass, it says that it is 55.8 AMUs. Okay, don't call it AMUs, call it grams. Now you have 1 mole of iron. The last example in your book is helium. Helium is in position 2. Okay, it says there that the atomic mass for helium is 4 AMUs. Don't call them AMUs, call them grams. Now you have 1 mole of that substance. Okay, I know it's a tiny bit strange to think this, because they didn't give you any context about where these numbers come from or how they got here in the book. It's too complex to go into how they discovered all of these for first year of chemistry, but if you study chemistry in college, you will learn about these. So right now, just believe it. It's one of those things that you're going to be applying in a minute. So here's another example, 2 more examples with pictures. Says an atom's mass in AMUs tells you how many grams it takes to have 1 mole of those atoms. So carbon and copper. If you look in the periodic table, carbon has an atomic mass of 12. So when you have 12 grams of that substance, you have 1 mole of that substance. 1 mole of carbon-12 equals 12 grams exactly. Copper, if you go to the periodic table, you see that the atomic mass for copper is 63.5. Well, when you have 63.5 grams of copper, you have 1 mole of copper. And 1 mole just means you have 6.022 times 10 to the 23 atoms. Okay. Here's another example. So we already talked about figure 5.3 on page 147, but I wanted to go over molecular masses. So this was the second box that you need to memorize and understand, and then we're going to apply it. But molecule's mass in AMUs tells you how many grams it takes to have 1 mole of those molecules. Here is your molecule, calcium carbonate. So if you go to the periodic table and find those atoms, and then you add their atomic mass units, remembering to multiply by 3 the oxygen because there are 3 of them, you'll see that it has a molecular mass of 100 AMUs. But don't call them AMUs anymore, call them grams. Then you have 1 mole of calcium carbonate. Okay, we'll do an example next. Example 5.6 on page 148. Okay, it says how many moles of fluorine atoms exist in a 50-gram sample of fluorine. That's your first half of this example. And the second one says people are encouraged to limit their table salt, sodium chloride, intake to 5 grams per day. How many moles of sodium chloride is that? And then you're going to do an extra practice problem on your own. So let's do the first half of this. What are they giving us? They say they want to know the number of moles. Okay, moles. That's the number of moles is what they're asking. For fluorine, if we have a sample of 50.0 grams of that fluorine, I just put the symbol. I don't know. Okay, there you go. Let's do that. So, 50.0 grams of fluorine. Okay. Grams of fluorine can be converted into what? Moles of fluorine. But to be able to do that, you need a conversion factor. You need to know how they are related. What do we know? We know that the same amount of grams as the atomic mass unit for that element will be 1 mole of that element. That's what it said on our definition. Okay, so 1 mole right here, 1 mole of fluorine of whatever substance, of whatever atom, has the same number of grams as the atomic mass unit that you find in the periodic table. So you go to the periodic table and you find the fluorine. And according to the periodic table, the fluorine is in position 9. The atomic mass for that fluorine is 19. So 19 grams of fluorine equals 1 mole. If another way you can do that, okay, another way of thinking of that, trying to think about this, you can go to the periodic table, so find fluorine, position 6, and say, okay, that's 19.0 AMUs. And I know that that is the same as 19.0 grams, which equals 1 mole for that substance. Okay, so if you have this amount in the periodic table, you have 1 mole of that substance, and those two are equivalent. That's how you do it. And once you have made that reasoning, then you can use your factor level method to convert it. So if you do the math here, you'll see that you get 2.63 moles of fluorine. That's your answer. Okay. 1 mole was 19, so in 50 grams you have 2.63 moles. And you're going to have to be able to do stuff like this. Let's look at the second example. Let me clean these for a minute. On the second half of the example, it says, people are encouraged to limit the salt to 5 grams per day. How many moles of sodium chloride is that? So we have 5.0 grams of sodium chloride with table salt. It's the same thing. So they want to know how many moles is that. So the grams of sodium chloride, we're going to have to go, and we want to know the moles. See, that's what they're asking. What are the moles? Well, in this case, we have a molecule. We know that 1 mole of that molecule has the same number of atomic mass units as grams for that molecule. So if I find the mass in AMUs for sodium chloride, I'll know the number of grams for that sodium chloride, okay? For 1 mole. 1 mole. That's my reasoning. So I need to find first, this is what I need to find. I need to find the molecular mass in AMUs for sodium chloride. Let's do that. The mass for sodium chloride equals, put an equal here. I go to the periodic table, find my sodium, and I see that the sodium has a mass of 23. I have one of them, 23.0 AMUs. And then I add the mass for the chlorine. The chlorine is in position 17, and according to the table is 35.5. So I have one of them. It is a 5. It's a very ugly 5, but it's a 5. So put in the calculator and you find that the molecular mass in AMUs is 58.5 AMUs. We just learned that instead of AMUs, we can call it grams. And then we have 1 mole of that substance. Okay, this is our conversion factor. This is our conversion factor right here. 1 mole of sodium chloride has 58.5 grams of sodium chloride. So that's what we need for this. 1 mole is 58.5 grams. Let me erase this, and then I'm just gonna finish the math here. So 5 times 1 divided by 58.5. If you do that, you'll see that you have 0.0855 moles of sodium chloride. This is your answer. Okay. Okay, review one more time. If you find the mass for that molecule in AMUs and you call it grams instead of AMUs, you have 1 mole of that substance. You have 6.0, whatever that number is, I don't have it memorized, as you can tell, 0.60.2 times 10 to the 23, okay, of that molecule of sodium chloride. Now, you try this. Number 10. You can find number 10 on page 573 in your textbook. I'm going to give you the answer, and if you get it right, move on. Just move on. The question says they want to know the moles. They give you the molecule, and you have 125 grams in the sample. So that's what they're asking. So what is the answer? The answer for number 10, this is number 10, okay, is 2.02 moles. Okay. If you got this, if this is what you got, you did it right, you're done. You can try again, but if you're still having problems with this, you can watch me solve these. Okay, the molecule is this molecule right here. Okay, this is the molecule they give you, and you have an amount. Let me change it to white. They give you 125 grams of the sample. This is what they give you. That's what you start with, and they want to know the number of moles. So you know that you want to get rid of those grams, and you want to end with moles. But to be able to do that, you need a conversion factor. You need to know how they are related. So you need to find out how many grams are in 1 mole. You know that you can find the molecular mass of whatever, okay, in AMUs and call it grams, and you have 1 mole of that substance. That is what we have been practicing. This is what we have learned. Okay, that's what we're applying. This knowledge we're applying. So the first thing I need to do is find the molecular mass for this sample. I need to find the molecular mass first in AMUs, call it grams, and I'll know my conversion factor. Let's do that. So molecular mass, I'm going to put it just like this because I don't have a lot of room. I need to find my hydrogen that's in position 1. So position 1, I have 2 of them. The mass for a hydrogen is 1.01 AMUs. And then I have a carbon. Carbon is in position 6, so 1 times 12.0. And then I have 3 oxygens, which is in position 8. And each one is 16. I forgot to put AMUs. Okay, AMUs. But you know, we're calculating AMUs. So if I do that, my molecular mass for this compound is 62.0 AMUs. And I said to you, okay, so we have 62.0 AMUs. We're doing this. We're trying to think this through, okay? So we can find our conversion factor. But now instead of this, I'm going to call it grams. So 62.0 grams. And that is 1 mole of that substance, which is this right here, is the conversion factor we were looking for. This is what we need. This is what we need to be able to solve this problem. So 1 mole is 62.0 grams. If I put this in my calculator, I'll get that 2.02 moles. Okay, that's where this came from. There you go. So this is our answer. This is our answer, and that's where it came from. Applying all the knowledge that we had. Okay. Okay, this week you're going to do experiment 5.1, so which is measuring the width of a molecule. And remember, if you have questions before you turn in your lab report, ask them. We're going to talk about it in class as well before you turn it in. More examples for you, page 152, other things that you need to be able to do with all the knowledge I have given you. So example 5.7. 5.7 reads like this. I'm going to the page. It says, a chemist determines that a sample of pure ammonia, they give you the formula, contains 12.331 moles of that ammonia. So what's the mass of the sample? Okay. Well, let me go to the board here. And let me get some white and write down what they are giving us. So they are saying that we have 12.331 moles of that ammonia. And what they want is the mass of the sample. So they want how many grams. They want to know the grams. Okay, that's the mass. That's the question. The grams. So how do we do that? How do we do that? Well, we always start with whatever they give us. And then we start thinking. Anytime that we convert stuff, we open our factor converting fraction here. So I know that I want to get rid of my moles of that ammonia and end with grams of, what did I do there? Sorry. Have to pay attention. Okay, why is it not? Maybe bigger. Okay, there you go. Grams of ammonia. That's what I want. But I need a conversion factor right here for this to work. I know that I can find how many grams are in 1 mole. If I have a molecule, I always can find how many grams are in 1 mole of that substance. So how do I do that? It's the same thinking that we have been doing. If I find the molecular mass in AMUs for that molecule, and then I call it grams, I know I have 1 mole of that substance. That's what we're thinking. This is our thinking process. Then let's find these. Let's find the molecular mass in AMUs for that specific molecule. Let's do that. So my molecular mass for ammonia equals, I need to find my nitrogen in the periodic table. That's in position 7. So position 7, it says that is 14. So one of them, 14, each one, AMUs, great. And then I need to add my hydrogens. I have 4 of them, and each one of them, position 1, is 1.01 AMUs. I put everything in the calculator, and if I do that, I find out that this molecule of ammonia has a mass of 17.0 atomic mass units. Okay. I'm gonna pick up a different color. Let's do it in blue. I'm gonna try to walk you through this thinking process. We just found out that this was 17.0 AMUs. And I said, if you call it grams, so I'm going to call it grams, 17.0 grams of ammonia, then I know that I have 1 mole of that ammonia. And now I have a conversion factor I can use. This is my conversion factor. This is what I needed. So I could put it here. 1 mole is 17.0 grams. Let me erase some of this because it's getting pretty cloudy. This is a video, so you are going to be able to go back and forth if you want. And pick up the grain again. So I just found out my factor that I needed to be able to do my computations here. And if I put this in my calculator, okay, I find that I have 2.10 times 10 to the 2 grams of ammonia in those 12.33 moles of ammonia. So this is my answer. That's what you needed to do. You're going to be doing some problems like these. So we are going to practice these and make sure that you understand this pretty well. Let me erase these, go back to instruction. So I want you to do 11, 12, and 13. And I'm going to give you the answers for each of them first. And if you don't get it, practice one more time, try it one more time, and then if you still don't get it, watch to see how it's done. So let's do that. Number 11, I'm going to put the answer here for 11. 11 is 19.1 grams of that calcium chloride. Okay, so that's your answer. Okay, how did we get here if you need to? The question was, what's the mass of this calcium chloride sample if you have 0.172 moles? So you started with a 0.172 moles. That's what they give you. Okay. And they want to know how many grams. That is the question. So we know we want to get rid of the moles. We don't want moles of this calcium chloride. We want to have grams. But to be able to do that, I need a conversion factor. Okay? And this is the thinking process. I know that in 1 mole of calcium chlorate, it's going to be the same amount in grams as these grams come from the molecular mass of that molecule. Okay, this is the conversion factor that I need. This is what I need. Maybe I should have make it bigger, a little bit bigger here. Grams. Okay, this is what I need to find. Okay. So I need to find the molecular mass. If I can find the molecular mass and change my units from AMUs to grams, I'll have my conversion factor, and then I can do this math right here. Let's find it. Let's find that molecular mass. So the molecular mass of this molecule equals, start adding. Let's find the calcium. Calcium is in position 20 in your periodic table, and there's one of them in this molecule. Each one is 40.1. Then we're going to add the chlorine. There are 2 of them, and each one in position 17 is 35.5. And I didn't put AMUs because I don't have a lot of room, but that's why we're calculating the AMUs. So the total is 111.1 AMUs. And I said, change these, call it grams. So 101.1 grams is 1 mole of that substance. Now I have my factor, and I can change my units here. So it says that 1 mole equals 111.1 grams. Do the math, okay? And then if you multiply this by this, and divide by 1 does not change anything, you're gonna get the 19.1 grams. And that's how you solve this one. Okay. Let's do number 12. So number 12. The answer for number 12 is 0.670 moles potassium chloride. Okay. So what did they give us? They give us 50 grams. The problem says that we have 50 grams, and they want to know the moles. So we know we want to get rid of our grams. Please put whatever you want to get rid at the bottom of your factor level method, and end with the moles. But I need a way to relate the two. Well, I start thinking about it. Well, we have learned in this module, we have learned that 1 mole of potassium chloride equals a certain amount of grams, and I can find those grams if I calculate the molecular mass of the molecule. In this case, this molecule. If I calculate the molecular mass and I call it, instead of AMUs, I call it grams, then I have a conversion factor. So let's do that. The molecular mass for this molecule is as follows. Let's find potassium. Potassium is in position 19. We have 1 of them, and each one of them is 39.1 AMUs. Okay. And then I only have one chlorine, so 1 times, and the chlorine is in position 17, 35.5 AMUs. Okay. If you do the math, your molecular mass in atomic mass units is 74.6 AMUs. And I said, okay, don't call it AMUs, call it grams. And then you have your conversion factor. Let's put it inside here. So 74.6. This is what I needed. This is how they are related. 1 mole equals 74.6 grams. And now I can put it here. Remember to put the right numbers with the right units. So 1 goes with a mole, and this goes with the grams. 74.6. And if you do the math, that's where you get the 0.670 moles. That's where it came from. Okay. 13. Number 13. They want to know how many. Oh, well, let me give you the answer first. 198 grams of carbon dioxide. Okay, that's your answer. If you got this, you did right. If not, try it again or watch the video. So here we go. They give you 4.51 moles of carbon dioxide, and they want to know the grams. So factor level method, moles at the bottom, trying to get rid of those, and we want to end with grams of CO2. Okay, but I need the factor, the conversion factor right here, and I need to know how they're related. The same idea as before. We need to find how many grams are in 1 mole, and we find the number of grams in 1 mole by finding the molecular mass in AMUs. Then not calling it AMUs anymore, call it grams, and you know how many grams are in 1 mole. So let's do that. The molecular mass of carbon dioxide equals, and this is an abbreviation, I just do it like that because I don't have a lot of room here. Okay. There's 1 carbon. Carbon is in position 6. Its atomic mass units is 12. And then I have 2 oxygens, position 6 if you need to find it. And that's 16. Do the math, and you'll see that the molecular mass for this carbon dioxide is 44.0 AMUs. And I said to you, don't call it that anymore. Call it grams. Well, I'm just going to put it like that. So call it grams. And now you know that you have 1 mole. When you call it grams, you have 1 mole of that substance. And that's the factor that you needed to be able to compute your answer. So 1 mole of carbon dioxide, this is all about carbon dioxide, okay, is 44.0 grams. If you do the math, you get the answer right here. 198 grams of carbon dioxide in 4.51 moles of carbon dioxide. Okay. Ask questions in class when we meet again if you still have problems with this. Well, using the mole concept in chemical equations, as I said to you, we're going to be using the mole concept quite a bit this year because we're going to be learning about stoichiometry very soon. So in chemical equations, and here's an equation, the coefficients, so if this nothing is a 1, but this 2, this another 2, and a 1, which appear to the left of each substance, tells you how many moles. So we talked about this. It could be molecules. You can be counting molecules. 1 molecule, 2 of these, gives you 2 of these and 1 of these. Yeah, you can do it that way. But when we do stoichiometry, we're going to work with moles. So now those coefficients, these numbers in front, okay, are going to be moles for you. Okay, The idea here is that you can have the equation is like a recipe. Okay, when you have an equation, it's a recipe to produce whatever you need to be producing. In this case, you're producing water and carbon dioxide. It's a combustion reaction because you have oxygen combining with hydrocarbon right here. Okay, but anyway, you know that this is a recipe, and you can double a recipe. You can double a recipe by multiplying by 2. And that means that everything needs to be multiplied by 2. So 2, 4, 4, and the 2. You have doubled the recipe. You can have a dozen. A dozen just means multiplying by 12. Well, you multiply everything by 12. 12, 24, 24, and 12. We talked about the mole being a quantity. You're multiplying by 6.02 times 10 to the 23. You can do that. That's why you can call these moles right here, because you can multiply by 1 mole. Okay. Now, these numbers are never grams. Don't confuse that, okay? Ever grams. Because when we are doing stoichiometry, you're going to be doing your math in moles. The recipe is going to be in moles. You're going to calculate things in grams. Yes, you're going to be calculating things in grams too. But when you're reading the recipe, you're going to be reading the recipe in moles. So do not get confused. You can call it molecules. You can call it moles. Now, let's see what we mean with all this information. Page 154, example 5.8. It says the decomposition of hydrogen peroxide into water and oxygen is described by the following chemical equation. So you have your hydrogen peroxide right here. It's breaking down, because the composition means it breaks down. And in this case, it's breaking down into water and oxygen. And it looks like they have already balanced it for you. You don't have to balance it. If the chemist begins with 2.4 moles of the hydrogen peroxide, how many moles of oxygen will be produced? Okay, how do we do this? You ready? Let's go to the whiteboard right here. Well, it's a blackboard, but I always call it the whiteboard, but no white. Let me write again the, oops, I don't want green. I just don't want green, white. The reaction. So 2 moles of hydrogen peroxide in the liquid form break down into 2 moles of water in the liquid form and oxygen gas. Okay, I told you that this is a recipe. Okay, you can read this as a recipe. It means 2 of these will produce 2 of these and 1 of these of oxygen. If there's no number, it means it produces. And what else did they give us? They give us if a chemist begins with 2.4 moles of these, so we have 2.4 moles of our hydrogen peroxide. They want to know how many moles of oxygen will be produced. How many moles are going to be produced? Because you need 2 to produce 1, but you don't have 2. You have 2.4. So how do we do this? Well, remember what I said to you. This is a recipe. A recipe means that you can put things together. The recipe says that 2 moles of hydrogen peroxide will produce 1, I'm putting it there, but usually you don't put it there, moles of oxygen. This is how the recipe reads. It says 2 will produce 1. Okay? Everybody so far so good? You're able to read these the same way as you say 2 will produce 2 of water, but it will produce 1 of oxygen. Very good. Now, let me get the white again. Okay, so we start always with what they give us. 2.4 moles of the hydrogen peroxide. We don't want moles of hydrogen peroxide. Anytime that we want to go from one thing to another, we use the factor level method. So open your fraction and put at the bottom what you're trying to get rid of. I'm trying to get rid of my moles of hydrogen peroxide. I don't want that. I want to know how many moles of oxygen this reaction will be able to produce if I start with 2.4. Well, I do have a way to relate them. I read the recipe. The recipe said 2 to 1. Well, let's put the numbers where they belong. The hydrogen peroxide is right here. There's a 2 in front. Then put 2 right here. The oxygen is here. It says 1. The oxygen is right here. Put the 1 here. Now do the math. So multiply 2.4 by 1 and divide by 2. Put in the calculator and you'll see that you get 1.2 moles of oxygen. Okay, another thing I need to go over here is significant figures. So for significant figures, I want you to know when we're counting moles, these are infinitely precise. They're infinitely precise. That means they don't count when you're counting significant figures. These conversion factors that you read from the recipe have nothing to do with it. So you need to start with looking at this one right here. And this one had 2 significant figures. That's why you ended with 2 significant figures. So keep this in mind, okay? These are infinitely precise. The coefficients right here are infinitely precise. Okay, let's look at the second part of the example. It says, if a chemist has 0.234 moles, and then they give you the molecule. I'm going to just write it down that way. I'm going to get white. So it says you have 0.234 moles of this molecule. How many moles of carbon will the chemist get by decomposing the sample? So they want to know the moles of carbon. That's the question. And this is a decomposition reaction. Well, you're going to have to work it on a bit more here. Decomposition means you're going to have to write your own recipe here. So decomposition means breaking down into its elements. So we're going to start with what they give us. We're breaking it down to carbon, to hydrogen, and to oxygen. And we remember that those two are diatomics. So they come in groups of 2. If we write the recipe, we know we have not balanced it yet. We need to balance this. That step of let's balance it. Well, balancing means counting atoms. Let's start with carbon. 1 times 2 equals 2. Carbon here is 1 times 1 equals 1. Okay, that's not going to work. So that means I'm going to have to put a 2 here. Let's start with 2. And that will become 2 times 1 equals 2. Okay, let's start with the next one. Hydrogen. So 1 times 6 equals 6. Here on this side, the hydrogen says 1 times 2 equals 2. That's not the same. So if I put a 3 here, I'm going to have 3 times 2 equals 6. So far, seems to be working okay right this minute. We'll see what happens with the oxygen. Okay, oxygen. 1 times 1 equals 1. Okay, and on the other side, we have oxygen. 1 times 2 equals 2. Well, no. I need 1/2 of these. Everybody sees that. I need 1/2 of these. So I'm going to have that 1, 2 as on the other side. Let me erase this part. We practice a lot of balancing equations, so this should not be too hard right now. You have been practicing this now for a while. So we know that we can only fractions like this. We need to get rid of those fractions. And how do I do that? I multiply everything by 2 to cancel the 1/2. So I have 2 I'm going to write it down. 4, 6, and then my oxygen. This is my recipe. Once I have balanced this decomposition reaction, I have a recipe. Now that I have a recipe, I can read the recipe. What am I trying to relate? Okay, let me get another color. I'm trying to relate this to this. Well, let's find it in our recipe. Here it is. This and this. Let's write this. Let's write it. So it says, the recipe says that 2 moles of this hydrocarbon, well actually, that's an oxygen, it looks like a 60, will produce 4 moles of carbon. Okay, this is what the recipe tells me. Now that I know how to put them together, I can do math. I'm going to have to get another page. Let's see how I do that. I think I can go here. Maybe. If it works. Okay, I found a different page. So I'm going to write down the factor here so you are aware of what I'm talking about. We read the recipe like this: 2 moles of this compound will produce 4 moles of carbon. Okay, great. Now that we have this, we have everything that we need. We go back to what they gave us. They gave us 0.234 moles of this compound. I don't want that. I want to get rid of my moles of this compound. And I want to know how many moles of carbon I can produce. Well, I use this to relate them because that's what the recipe said. It said 2 moles will produce 4. So let's make sure that we put the numbers in the correct place. The 2 goes with this compound, so I'm putting a 2 here, and the 4 goes with the carbon. So the 4 goes at the top. And I do the math, and I get 0.468 moles of carbon. That's your answer. Okay. And once again, the 4 and the 2 infinitively precise, so they don't count when we count significant figures. And in this case, 1, 2, 3. So 1, 2, 3. And now it's your turn to do one of these on your own. You're going to do number 8. Okay, I'm going to give you the answer for number 8. And if you got it, just move on. If not, check to see how it's done. Your answer should be 211 moles of carbon dioxide. Okay, so try again if you didn't, or watch how this is done. Let me read it to you. It says, in the combustion, so combustion, they don't even give you the reaction, so you're going to have to come up with that combustion. In the combustion, they give you the molecule, how many moles of carbon dioxide will be made when you have 13.2 moles of that compound when they are burned. So the first thing we need to do is write down what they give us. We know it's a combustion, so immediately in your head you're combining with oxygen. And you know there are 2 products to combustion, carbon dioxide and water. Now you just wrote this. It's not it's not balanced. So you're gonna have to balance this. So let's start with that. Carbon 1 times 16 equals 16. Carbon here, 1 times 1 equals 1. That's not going to work, is it? Let's put a 16 right here, and then I'm going to have 16 times 1 equals 16. There you go. And hydrogen. So hydrogen is the next element that we need to make sure it's balanced. So 1 times 24 equals 24. On the other side, we have 1 times 2 equals 2. That's not balanced either, but if we put a 12 here, then I'm gonna have 12 times 2 equals 24, which makes it balanced. We have now the oxygen to do. 1 times 2 equals 2, and oxygen on this side is 12 times 1 equals 12. Well, do we have any more? I forgot to put this one right here, so yeah, we do have more. So 16 times 2 equals 32. So, sorry, 36. Gosh, I'm getting tired here. Maybe I should finish tomorrow. Let's see, 36, 32. I don't know what I'm talking about. Okay. Well, we have a problem, don't we? That is not gonna work. Let's add it up first. So that's how do I make that 2 into 44? Well, if I multiply this by 22, so 22 times 2 equals 20. 44. I mean 40. 44. Okay. I don't like the way this is right here. It's driving me nuts. So let me erase these and put it nicely. Okay. 22 oxygens. Okay. Now that we have balanced this balanced. Okay. Now this is a recipe. If it was not balanced, it was not a recipe. It was not correct. Now that I have a balanced recipe, I can read the recipe and relate what I need to relate. They're warning me to find out how many moles of carbon dioxide. So, given this, how many moles of carbon dioxide am I producing? So I know that they're related like this. 1 mole of this molecule will produce 16 moles of carbon dioxide. So this is the conversion factor that I'm going to have to use when I do my math, my computations. Start with the number they give you. Let me put white again. So you start with 13.2 moles of that molecule, and open your factor, put down here what you want to get rid of. So you're going to get rid of your moles of this molecule. You don't want these. You're trying to find carbon dioxide, and you know that you want your carbon dioxide, your moles of carbon dioxide is what you want to end with. This is going to be gone. Goodbye. Okay, how are they related? According to our table right here, it says that 1 mole of this molecule will produce 16 moles of carbon dioxide. Just make sure that the numbers go with the right molecules. So once you do that, you put in the calculator, 13.2 multiplied by 16 divided by 1 is that 211 moles of the carbon dioxide that needed to be your answer. So that's how it's done. Okay, let me erase this and go back here. Now, make sure that you know your homonuclear diatomics. You need to know what elements exist in groups of 2. There are 8 of them. This may help you or not. Some people use different devices to remember things. It makes the shape of a 7. Those elements are in the shape of a 7, except for that hydrogen right there. If that helps you remember where they are. But remember that you need to know which ones are mononuclear diatomics, because when you write chemical equations, you immediately have to put the subscript 2 to be able to balance the chemical equations and do your chemistry. Okay. That's it. Just make sure that you have a photocopy of Apologia's periodic table, the one that is in your textbook, okay, page 75 or the front of your textbook as a separate page, because you're going to be using it a lot. Okay, this ends the second half of Module 5. So read your textbook and add to your notes. Review examples if you need to. Work on your own as you encounter them. Correct them as you encounter them, because you don't want to make the same mistake over and over. Study for your conceptual weekly quiz. Do any labs assigned for this section. Review questions and self-correct. I gave you an answer key, so try to do it one more time before you look at the solutions manual. And do also all the practice problems and self-correct. Okay, that's it.